Thanks for coming. We're talking about a very big milestone today. This is very exciting news. We have sent the GDS, which is the image of our chip, to TSMC in order to begin fabrication of our custom processor for zero-knowledge proofs. This is especially big because we're going to go into all of the things that made this very hard, made the last few months a big challenge for the team. So the first thing that anyone asks me, I'm Michael, I'm CEO of Fabric. We build these ZK processors, and most people think that it's a ZK ASIC, right? So the thing about ASICs is it's an application-specific integrated circuit, right? And so people think that, hey, you have to tape out a new chip anytime the proof system changes, right? In fact, the OG post that started the whole field of ZK hardware was this paradigm blog post where they said, basically these algorithms change all the time, and so you're going to need really flexible hardware like GPUs and FPGAs. And indeed, that is what people do. So our predecessors in the space have done really incredible work in accelerating things on GPU, accelerating things on FPGA. Hats off to what they've been able to accomplish on those platforms. And it's accelerated ZK orders of magnitude beyond where it was in 2021, 2022. It's amazing that we've already gotten to real-time ZK, even without custom silicon. That's pretty amazing. And so the question is do we continue accelerating with general purpose hardware, or do we use ASICs? And it really turns out it's kind of like an optical illusion. It's kind of the answer is neither, okay? So people always ask me what determines the overhead of a general purpose processor? What is the essential overhead of programmability? And it's a really good question. On the left you see kind of a typical GPU, right? So the first thing about a GPU is GPUs are made for graphics and they're made for AI, right? And so most of the ALUs on the GPU, the arithmetic logic units, the actual circuitry that does arithmetic, does math, right? It's dedicated to floating point math, which is near useless for zero-knowledge proofs. So all of that area on the chip is actually wasted, right? And so the crypto stuff is only running in some units some of the time, right? And so this is the fundamental reason why GPUs are unsuited to ZK, right? And so they beat CPUs because you have a lot more cores, but you still don't have that many dedicated to actual cryptography, right? And so the thing about creating a custom processor is you can saturate all of the units all of the time if you design your instruction set cleverly enough so that zero-knowledge proofs specifically run really fast on it, right? And so that's what we set out to do. And the bet that we made was that we could share enough of the circuitry between all of these different operations that we could actually make sure that none of the logic was wasted, or close to none, maybe half, right? But if your overhead is low enough, then actually there are so many other components outside the silicon, right? You need external memory, you need a board, you need a heatsink, you need power regulators, you need all these other things that ultimately the impact of that general purpose overhead is close to nothing. Right? And so that's what Fabric was founded to do. Our thesis is that every generation of computing is defined by some sort of breakthrough microprocessor, which is defined as a general purpose computing platform that can do multiple workloads of a certain kind, right? And so we basically think that the coming era of prog crypto, ZK, FHE, even the future stuff like witness encryption, IO, functional encryption, all of this is going to run on massively parallel prog crypto silicon, and that's what we built the VPU to do. We basically built the VPU to be kind of the CUDA and the NVIDIA GPU of cryptography. Now, we finally did it. A lot of people called us insane at the beginning of this journey. I remember we had our first conversations were at SBC 2022. And a lot of people told me, why don't you just build a TEE instead? Which it turns out we're doing that next. But we actually did the insane thing first. We built the first programmable cryptography chip in the world. It is on TSMC 12 nanometer, and it has these massively parallel vector lanes, specifically with cryptographic instructions, right? So You want to do a Goldilocks multiply and accumulate, we can do that in one instruction. And there's actually room left over to do another shift add at the same time, right? So we've built this instruction set in such a high efficiency way that you can actually saturate most of the gates most of the time on all of the programmable cryptography workloads. So it supports, all of the different ZK-VMs that you've probably heard about today, and it supports probably the next generation of ZK-VMs well into the future as well. And one thing I want to emphasize is that this is not just about taping out a chip. Taping out a chip is an endeavor involving like 90% other tasks outside of taping out a chip. You have to design the board the chip goes on. You have to do the thermal simulation for the board. You have to do the signal integrity simulation, right? Like, you have to do the package design that's on the left. You have to build a compiler for the chip. Thomas over there in the audience has done an amazing job with his team of building a general purpose compiler for a general purpose ZK chip. So basically, we can take Go, we can take high-level languages, we can even take languages like AirScript, and we can like directly compile them to vectorized VPU code that runs really, really fast, faster than GPU, cheaper than GPU. And another really interesting thing is just how hard it is to beat NVIDIA even when they don't even care about the use case that you're targeting. So the RTX 5090 is on 3 nanometer technology, we're on 12. And so the density of the transistors tends to scale as the square of the nanometers. And so we're actually like 16x disadvantaged on the density of the transistors. It's also a bigger chip, and it also runs at over twice the frequency. And so even if like we're focused 100% of this chip on cryptography, it actually turns out that like it's very hard to beat NVIDIA. We have like by default 100x disadvantage. And we're very proud to say that our team has actually beaten NVIDIA on ProCrypto. And so here are some use cases across the board. The left-hand side, RISC-0, one of our beloved partners, one of the first ones to believe in us because they're also ex-hardware people. We've been able to achieve a very high performance per dollar versus advanced stage NVIDIA GPUs. And it actually applies across the board. No matter where you look, our cost performance actually far exceeds that of advanced stage GPUs. And the really cool thing is that there are a lot of caveats that we basically have been able to solve, right? And so what a lot of people ask us about is, what about memory hardness? What about data movement? We speed it up despite that. And there's a lot of like explanation that I can go into about how we do that. What about irregular stuff? Like, what about eval check, right? Like, eval check is like RISC-0's constraint evaluation. And like, this is one of the first things that they asked us because it was the hardest thing to accelerate because it is not an NTT, it is not a Poseidon, it's this really complicated mush, right? And we speed that up too, And what about binary fields, right? Like, we actually implemented a tower field sum check, and we even have instructions for binary fields, and it can go much faster than FPGAs. And so basically across the board, no matter which field you're using, which proof system you're using, whether you're using elliptic curves, whether you're using hash-based commitments, whether you're using this or that, we can speed all of it up. And we are actually building it natively into Plunky 3 so that any Plunky 3 circuit automatically translates to a VPU speed up. And so, what we're really releasing is not just the hardware, it's not just the chip, it's a full stack solution for operators, right? So we have multiple compilers, we have multiple kernels like Poseidon, like NTT, we have multiple libraries, and we're also introducing a cloud platform that people are gonna be able to rent these VPUs by the hour from. So it's really exciting, we're doing this as a startup of like only dozens of people, right? And we're basically replicating that whole hardware software stack that you're used to. NVIDIA, AWS, all the niceties of that, the Plunky 3 experience, right? Like, we're bringing that to you with new silicon. And this is what it looks like. This is kind of a marketing render, so don't believe it too much. We actually had a physical unit of this that we showed off a few days ago at our demo day. But this is the server, and it has a bunch of like VPU 8060 cards, which are these. And basically, you can rack them up, you can install them en masse. And a little bit about the architecture that powers all of this, right? So we basically have a bunch of these cores, and each core just has a lot of lanes, right? It's kind of like RISC-V vector extensions. It's kind of like AVX 512, but these instructions are basically built natively for modular arithmetic, and it has a RISC-V as well on the chip. And so this is another exciting thing because a lot of people ask us about the programming model, and they also ask us about PCIe and like the bandwidth bottleneck and things like that. Well, we have 11 terabytes per second of bandwidth on the chip in our network on chip, which we designed from scratch, to be able to move data super fast from that built-in CPU, which can boot Linux. So it's a standalone Raspberry Pi-like processor that runs Rust, that has a full Rust environment, and then basically any VPU code you want to call, it's just a function call away. And so there you have it, the VPU. Thank you all.